Hello and welcome everyone. So from today onwards we will discuss about the ring theory. Okay, ये पहला लेक्चर है. In this lecture we will discuss about the introduction of ring theory. Introduction में हम बात करेंगे कि सिलेबस क्या होता है, क्या क्या चीजें हम पढ़ने वाले हैं. ठीक है, from the next lecture onwards we will start our ring theory. Okay, so let's first see the syllabus. What is syllabus of the ring theory? So first we will discuss about the introduction of ring. Introduction of ring. Okay, in this unit introduction of ring we will discuss about the definition of ring. ring का definition क्या होता है, फिर उसके बाद में ring की कुछ examples, उसके बाद में commutative ring क्या होता है, right? commutative ring with unity क्या होता है, जिसको अपन CRU बोलते हैं, CRU क्या होता है ना, unit element क्या होता है, zero divisors क्या होते हैं, characteristic of a ring क्या होता है, Gaussian ring of Gaussian integers क्या है, वो सारी चीजें अपन इस यूनिट में बात करेंगे. Then in the second unit we will talk about the subrings and ideals. Subrings and ideals. ओके, नेक्स्ट लेक्चर में अपन बात करेंगे कि सबरिंग्स क्या होते हैं, आइडियल्स क्या होते हैं, फिर उनके एग्जांपल्स एंड देन कुछ प्रॉपर्टीज सबरिंग्स एंड आइडियल्स की. ओके, जैसे फॉर एग्जांपल अगर दो सबरिंग्स हमारे पास है तो क्या उनका सबरिंग एडिशन करने पर भी सबरिंग होगा या नहीं होगा, राइट? कब सबरिंग हो सकता है उनका एडिशन, राइट? आइडियल्स की क्या प्रॉपर्टीज है, फील्ड के पास कितने आइडियल्स होते हैं, वो सारी चीजें हम डिस्कस करेंगे. देन इन द थर्ड यूनिट वी विल टॉक अबाउट द इंटीग्रल डोमेन एंड फील्ड्स. इंटीग्रल डोमेन and field. Okay, integral domain and field. Okay, then in the fourth lecture, third lecture में अपन इंटीग्रल डोमेन, जीरो डिवाइजर्स क्या होते हैं, इंटीग्रल डोमेन क्या होता है, इंटीग्रल डोमेन के क्या एग्जांपल्स हो सकते हैं, फिर उनके क्या क्या प्रॉपर्टीज हैं, फील्ड क्या होता है, फील्ड की क्या प्रॉपर्टीज है, जैसे फील्ड के पास कितने आइडियल होते हैं, फील्ड के पास दो आइडियल होते हैं, अगर किसी रिंग के पास दो आइडियल है तो क्या वो फील्ड बनेगा, अगर CRU के पास दो आइडियल्स है तो क्या वो फील्ड बनेगा, और बहुत सारी चीजें हम इस यूनिट में डिस्कस करेंगे. देन इन द नेक्स्ट यूनिट वी विल टॉक अबाउट द मैक्सिमल आइडियल्स. Maximal ideals and prime ideals. What are maximal and prime ideals? Okay, मैक्सिमल आइडियल एंड प्राइम आइडियल की डेफिनेशन, एग्जांपल्स करने के बाद फिर हम इस पे बात करेंगे कि कब प्राइम मैक्सिमल हो सकता है, कब मैक्सिमल प्राइम होता है, राइट? उन सारी चीजों के बारे में इस यूनिट में हम बात करेंगे. देन क्वोशिएंट रिंग एंड होमोमॉर्फिज्म. इन द फिफ्थ यूनिट वी विल टॉक अबाउट क्वोशिएंट रिंग एंड होमोमॉर्फिज्म. ओके, इस यूनिट में अपन बात करने वाले हैं कि अगर हमारे पास आइडियल है, रिंग है, तो अपन क्वोशिएंट रिंग डिफाइन कर सकते हैं. क्वोशिएंट रिंग क्या होता है उस पर बात करेंगे, उसके एग्जांपल्स डिस्कस करेंगे, राइट? फिर बहुत सारी इंपॉर्टेंट प्रॉपर्टीज हैं क्वोशिएंट रिंग से रिलेटेड, राइट? जैसे फॉर एग्जांपल अगर आप क्वोशिएंट रिंग के बारे में जानते हो, वेदर दिस इज इंटीग्रल डोमेन और फील्ड, देन यू कैन टेल अबाउट द ring, ideal actually, whether this is a prime ideal or maximal ideal of the ring, है ना? In the same way homomorphism is also important. इसी यूनिट में अपन होमोमॉर्फिज्म के भी ऊपर बात करेंगे. रिंग होमोमॉर्फिज्म एक्चुअली क्या होता है, क्या क्या उसके एग्जांपल्स है, कर्नल ऑफ ए होमोमॉर्फिज्म क्या होता है, राइट? फिर कर्नल आपका कब आइडियल बनता है ना, या फिर कर्नल हमेशा ही वैसे आइडियल बनता है किसी भी रिंग होमोमॉर्फिज्म का, आइडियल्स आपके कर्नल बनते हैं, वो सारी चीजें अपन इस लेक्चर में हम बात करेंगे. काउंटिंग ऑफ होमोमॉर्फिज्म उस पर बात करेंगे. फिर 4 homomorphism theorems are there, we will talk about that as well. So what are first isomorphism theorem, second isomorphism theorem, third isomorphism theorem and fourth isomorphism theorem. फिर उनके कुछ एग्जांपल्स कैसे हम इन थ्योरम्स को यूज कर सकते हैं, उस पे हम इस यूनिट में बात करने वाले हैं. इन द सिक्स्थ यूनिट वी विल टॉक अबाउट द पॉलिनोमियल रिंग्स. ओके, पॉलिनोमियल रिंग्स. पॉलिनोमियल रिंग्स में सबसे पहले तो पॉलिनोमियल रिंग के बारे में ही बात करेंगे कि पॉलिनोमियल रिंग कैसे बनाते हैं. फिर पॉलिनोमियल रिंग में बहुत सारे इंपॉर्टेंट रिजल्ट्स हैं. एक्चुअली क्वोशिएंट रिंग का कैसे अपन यहाँ पे यूज कर सकते हैं, वो सारी चीजें हम देखेंगे. इररिड्यूसिबल पॉलिनोमियल्स क्या होते हैं, रिड्यूसिबल पॉलिनोमियल्स क्या होते हैं, रिड्यूसिबल पॉलिनोमियल्स हम डिफरेंट फील्ड्स पे कैसे चेक कर सकते हैं, या फिर डिफरेंट रिंग्स में भी बोलना चाहिए कि कैसे चेक कर सकते हैं. आइंस्टीन्स क्राइटेरियन क्या है, साइक्लोटॉमिक पॉलिनोमियल्स क्या होते हैं, है ना? गैल्वा फील्ड भी इवन इसी चैप्टर में हम डिस्कस करेंगे, है ना? वो सारी चीजें क्या है, ये सब बात करने वाले हैं हम इस चैप्टर में. एंड नेक्स्ट यूनिट इज ED, PID एंड UFD. ED, PID and UFD. ED stands for Euclidean domain and PID stands for principal ideal domain. Unique factorization, UFD is nothing but unique factorization domain. तो इन सब के ऊपर हम बात करने वाले हैं, इनकी डेफिनेशंस, एग्जांपल्स, फिर इनमें क्या रिलेशन है, जैसे कब EID PID होगा, राइट, कब ED PID होगा, कब PID ED होगा, कब PID UFD होगा कि नहीं होगा, UFD PID होगा कि नहीं, PID UFD होगा, राइट, PID ED होगा कि नहीं होगा, ED ID होता है कि नहीं, इंटीग्रल डोमेन होता है कि नहीं, फील्ड यूक्लिडियन डोमेन होता है कि नहीं, एक पॉलिनोमियल रिंग कब यूक्लिडियन डोमेन होगा अगर हम रिंग कैसा कंसीडर करें, उन सब चीजों पे हम इस लेक्चर में डिस्कस करने वाले हैं. एंड इन द नेक्स्ट यूनिट वी विल टॉक अबाउट द फील्ड थ्योरी. ओके, फील्ड थ्योरी में अपन क्या क्या बात करेंगे. फील्ड थ्योरी में एक्चुअली फील्ड एक्सटेंशन क्या होता है, डिग्री ऑफ फील्ड एक्सटेंशन क्या होता है, फाइनाइट फील्ड क्या होते हैं, उन पे बात करेंगे. फिर उसके बाद में अलजेब्राइक एक्सटेंशन क्या होता है, स्प्लिटिंग फील्ड क्या होता है ना. फिर उसके बाद में नॉर्मल एक्सटेंशन क्या होता है, सेपरेबल एक्सटेंशन क्या होता है, गैल्वा एक्सटेंशन क्या होता है, उन सारी चीजों पे डिस्कस करेंगे. बहुत सारे इंपॉर्टेंट रिजल्ट्स भी है रिलेटेड टू फील्ड, उन सब पे डिस्कस करने वाले हैं. तो ये पूरा हमारा सिलेबस है रिंग थ्योरी का, जो कि अपने को कंप्लीट करना है. फ्रॉम द नेक्स्ट लेक्चर ऑनवर्ड्स वी विल स्टार्ट इंट्रोडक्शन टू रिंग, और रिंग का डेफिनेशन एंड वो सारी चीजें हम नेक्स्ट लेक्चर में डिस्कस करेंगे. ठीक है, सो दिस इज ऑल अबाउट दिस लेक्चर, इट इज ऑल अबाउट द इंट्रोडक्शन ऑफ द रिंग. ओके, इन द नेक्स्ट लेक्चर वी विल स्टार्ट विद द डेफिनेशन ऑफ ए रिंग. ओके, थैंक यू एवरीवन एंड लेट्स सी यू इन द नेक्स्ट लेक्चर. थैंक यू वंस अगेन, टेक केयर. Hello and welcome back everyone. So let's start with introduction to ring from in this lecture. So if we talk about the prerequisites for ring theory, to study ring theory, the prerequisites is only group theory. If you have some basic knowledge about group theory, you can just start with the ring theory. तो ring theory start करने के लिए हमें क्या होना चाहिए, basic knowledge group theory के बारे में होना चाहिए. एंड अगर मैं डेफिनेशन की बात करूं, सो जो मैं बोलता हूं कि ग्रुप थ्योरी का बेसिक नॉलेज आपको होना चाहिए, तो सपोज दैट कम से कम आपको डेफिनेशन के बारे में तो पता ही है, राइट. सो डेफिनेशन ग्रुप का क्या होता था, ए नॉन एम्प्टी सेट जी with a binary operation, or you can say an operation star, we say that it is a group, and we say that it is a group if it has certain properties, right. What are those properties? Z with the operation star, it should be closed, or you can also say that star should be a binary operation on G, right. This was the first property. The second property was it should have a associative property, right. The star should have associative property on G. If you consider any three elements and you do the operation in any order, do the operation of first two elements, then do the operation with the third elements, or you can do the operation with the two last elements first and do the operation then with the first element, you should get same, right. So associativity should be there with respect to star operation. The third is existence of identity element. There should be an element E in G such that if we do the operation with any other element of the G or any element of the G, it should again give back to the same elements whatever that element was, right. We did the operation with the A element, right. So there should be an identity element, existence of inverse property, right. For any element A, there should be an B element such that A star B should be identity element, right. For any element A, we should have an identity element, we should have an inverse element, right. So if a non-empty set G with operation star has all these four properties, we say that G with operation star is a group. In the same way, if we have, let me say, a non-empty set R together with two binary operations, one is addition and the another one is multiplication, and they are just notations. You should keep this in your mind that they are just notations. मतलब अगर R non-empty set है, addition और multiplication की जगह पे कुछ और भी ऑपरेशन हो सकते हैं, राइट. अगर कोई भी आप ऑपरेशन कंसीडर करते हो एडिशन की जगह पे, इट शुड बिहेव लाइक एडिशन. मल्टीप्लिकेशन की जगह पे अगर कोई ऑपरेशन कंसीडर करते हो, देन इट शुड बिहेव लाइक मल्टीप्लिकेशन, राइट. ऑपरेशन कुछ भी हो सकता है. इसको अपन क्या करेंगे, अपन रिंग बोलेंगे इफ इट हैज सर्टेन प्रॉपर्टीज। व्हाट आर दीज प्रॉपर्टीज, वी विल सी दैट, राइट। एडिशन के रिस्पेक्ट में कुछ प्रॉपर्टी होंगी, कुछ मल्टीप्लिकेशन के रिस्पेक्ट में प्रॉपर्टी होंगी, क्योंकि दो ऑपरेशंस है तो दोनों के लिए भी कुछ प्रॉपर्टीज होंगी। तो उन प्रॉपर्टी को अगर ये सेटिस्फाई करता है देन वी कॉल इट एज अ रिंग। तो ग्रुप में एक ऑपरेशन था, यहाँ पे दो ऑपरेशन है, बस बाकी चीजें लगभग सेम ही है ना। सो लेट्स डिफाइन व्हाट इज अ रिंग। Okay. A non-empty, let me write it first, definition. A non-empty set R with two operations, with two operations। अभी मैं बाइनरी ऑपरेशन नहीं बोल रहा हूं, क्योंकि जब आप प्रॉपर्टीज लिखोगे तो उसमें ही बाइनरी ऑपरेशन आ जाएगा। टू ऑपरेशंस, कॉल इट एज एडिशन एंड मल्टीप्लिकेशन, राइट, एंड मल्टीप्लिकेशन। A non-empty set R with operation addition and multiplication, okay, that is R with operation, let me say addition and multiplication, is said to be a ring, is said to be a ring if it has, let me say, if it has following properties. Properties, what are those properties? The first property, let me write it as a A. The first property is R with operation addition, R with operation addition, this should be an abelian group, this should be an abelian group। अब जब आप इसको abelian group बोलते हो तो इसके साथ पांच प्रॉपर्टीज आ गई, राइट। कौन सी पांच प्रॉपर्टी? The first property is R with operation addition, this should be closed, right, or let me say in other words, you can say that addition should be closed, or R should be closed with respect to operation addition. It means that A plus B should be inside R for all A comma B belongs to R। BC प्रॉपर्टी को आप ऐसे भी बोल सकते हो, R is closed with respect to operation addition, या फिर R with operation addition is closed, या फिर addition is a binary operation, right, कैसे भी बोल सकते हो। And the second property is associativity होनी चाहिए, A plus B plus C should be same as A plus B plus C, A plus B plus C for all A comma B comma C, A comma B comma C belongs to R। मतलब किसी भी ऑर्डर में अगर आप ऐड करते हो तो कोई फर्क नहीं पड़ना चाहिए, ए बी को पहले ऐड कर लो फिर सी को ऐड करो, या फिर बी सी को ऐड करने के बाद ए उसमें ऐड करा दो, राइट, दिस वुड बी सेम। एंड द थर्ड प्रॉपर्टी इज एग्जिस्टेंस ऑफ आइडेंटिटी एलिमेंट, देयर एग्जिस्ट, लेट मी से 0 बिलोंग्स टू आर। एडिटिव आइडेंटिटी को किससे डिनोट करेंगे? 0 से। इट कैन बी एनी अदर, राइट। अगर जैसे मैट्रिसेस का आप रिंग कंसीडर करोगे तो वहां पे 0 क्या होगा? 0 मैट्रिक्स इज द 0 एलिमेंट, राइट। सो 0 बिलोंग्स टू आर सच दैट, क्या प्रॉपर्टी होना चाहिए इसके पास? अगर मैं किसी भी एलिमेंट में लेट मी से ऐड करूँ a प्लस 0 इक्वल्स टू 0 प्लस a इज इक्वल्स टू a फॉर ऑल a बिलोंग्स टू r, राइट। एंड द फोर्थ प्रॉपर्टी इज हर एक एलिमेंट के पास इनवर्स होना चाहिए विद रिस्पेक्ट टू ऑपरेशन एडिशन। जब इसको आप ग्रुप बोल रहे हो, अबेलियन ग्रुप बोल रहे हो, तो सारी ग्रुप की प्रॉपर्टी उसके साथ कम्यूटेटिविटी भी होनी चाहिए, राइट। तो लास्ट प्रॉपर्टी ग्रुप के लिए क्या होती है? फॉर ऑल a बिलोंग्स टू r देयर एग्जिस्ट b बिलोंग्स टू r such that a plus b is equals to 0, right? तो किसी भी एलिमेंट ए के लिए उसका इनवर्स बी एग्जिस्ट करना चाहिए, एंड बी इज एक्चुअली नथिंग बट माइनस ए हियर, राइट। ओके फाइन। एंड द फिफ्थ प्रॉपर्टी इज कम्यूटेटिविटी, राइट। a plus b should be same as b plus a for all a comma b belongs to r, right। तो ये हो गया r with operation addition, this should be abelian group, means it should satisfy all these 5 properties। ये तो हो गई एडिशन के लिए प्रॉपर्टी। अगर इतनी सारी होगी 5 प्रॉपर्टी तो उसको बोलेंगे हम R with operation addition is a abelian group। The second, there are some properties we need with respect to operation multiplication, and those are R with operation multiplication, this should be a semi group। मतलब R with operation addition हमें ग्रुप चाहिए, पर R with operation multiplication सेमी ग्रुप भी होगा तब भी चलेगा, ग्रुप नहीं चाहिए, राइट। सेमी ग्रुप के लिए क्या क्या प्रॉपर्टी होती है? फर्स्ट प्रॉपर्टी इज इट शुड बी क्लोज, मतलब A मल्टीप्लिकेशन B शुड बी इनसाइड R फॉर ऑल A comma B belongs to R। नेक्स्ट प्रॉपर्टी क्या होना चाहिए? एसोसिएटिविटी, ए मल्टीप्लीकेशन बी multiplication c should be same as a multiplication b multiplication c for all a b c belongs to r. ये दो प्रॉपर्टी केवल मल्टीप्लिकेशन के लिए होनी चाहिए. देन c इज डिस्ट्रीब्यूटिव प्रॉपर्टीज. अब कुछ प्रॉपर्टीज ऐसी भी होनी चाहिए जो दोनों साथ में सेटिस्फाई करे. डिस्ट्रीब्यूटिव प्रॉपर्टीज, अब दो ऑपरेशन है तो कुछ तो एक साथ होना चाहिए ना रिलेशन. डिस्ट्रीब्यूटिव प्रॉपर्टीज, व्हाट आर डिस्ट्रीब्यूटिव प्रॉपर्टीज? द फर्स्ट प्रॉपर्टी इज multiplication actually should be distributive over addition from left as well as right. A multiplication b plus c should be same as a multiplication b plus a multiplication c for all a b c belongs to r. and ये multiplication आपका राइट से भी डिस्ट्रीब्यूट होना चाहिए. मतलब a प्लस बी अगर मल्टीप्लीकेशन c करूं देन इट विल बी सेम एज a मल्टीप्लीकेशन c प्लस b मल्टीप्लीकेशन c फॉर ऑल a b c बिलोंग्स टू r. अब अगर आप इंटीजर्स में इन प्रॉपर्टीज को देखोगे तो बहुत ही ऑब्वियस सा फील होता है राइट कि ऑल दीज आर ऑब्वियस. बट अगर आप इंटीजर्स के अलावा और रिंग्स कंसीडर करोगे, ऑपरेशंस एडिशन और मल्टीप्लिकेशन के अलावा कुछ और कंसीडर करोगे तो थोड़ा सा आपको वेरीफाई करनी पड़ेगी, चीजें देखनी पड़ेगी कि हाँ ऐसा होता है या फिर नहीं होता है. ठीक है, तो अगर कोई आर नॉन एम्प्टी सेट है, एडिशन विद ऑपरेशन मल्टीप्लिकेशन उसके साथ दो ऑपरेशन के साथ में, ये प्रॉपर्टी सारी प्रॉपर्टी कितनी हो गई? 5 ये प्रॉपर्टीज, 2 ये 5 and 2 7 and 2 9. ये 9 सारी प्रॉपर्टी अगर कोई सेट नॉन एम्प्टी सेट आर विद ऑपरेशन एडिशन एंड मल्टीप्लिकेशन सेटिस्फाई करता है देन वी से दैट इट इज अ रिंग. ओके, नाउ लेट्स लुक एट सम एग्जांपल्स. ओके, द फर्स्ट एग्जांपल कैन बी z with the operation addition and multiplication is a ring. Is it a ring? This is a ring, right? Why this is a ring? और यहाँ पे ये जो addition है आपका, this is usual addition inside integers. Multiplication is usual multiplication, right? Okay, so this is a ring. Why this is a ring? Because if you check the first property, z with the operation addition, this is an abelian group. अभी इसको वेरीफाई करने की मुझे नहीं लगता कि जरूरत है क्योंकि ग्रुप आप लोगों ने मैं मानता हूं कि पढ़ा है राइट. इट इज एन अबिलियन ग्रुप, सारी अबिलियन ग्रुप की प्रॉपर्टीज इसके पास होते हैं. द नेक्स्ट इज इट इज अ सेमी ग्रुप आल्सो. जेड विद द ऑपरेशन मल्टीप्लिकेशन इट इज अ सेमी ग्रुप. दिस इज ये सेमी ग्रुप भी है. सेमी ग्रुप के लिए क्या लीजिए? क्लोज्ड विद रिस्पेक्ट टू मल्टीप्लिकेशन एंड जेड इज क्लोज्ड विद रिस्पेक्ट टू मल्टीप्लिकेशन. You take any two integers, you multiply them, again we will get some integer, right? So it is closed. And associativity is also there. 3 आप इंटीजर ले लो, किसी भी ऑर्डर में मल्टीप्लाई करो, we will get the same. पहले 2 को मल्टीप्लाई करके फिर लास्ट वाला मल्टीप्लाई करो, या फिर पहले लास्ट वाले को 2 को मल्टीप्लाई करके फिर पहले वाले के साथ मल्टीप्लाई करो. कोई फर्क पड़ता है? नहीं पड़ता है, राइट. सो इट इज सेमी ग्रुप आल्सो एंड वी विल हैव डिस्ट्रीब्यूटिव प्रॉपर्टीज, राइट. जेड विद द ऑपरेशन एडिशन एंड मल्टीप्लिकेशन हैज डिस्ट्रीब्यूटिव प्रॉपर्टीज एज वेल. डेली लाइफ में रोज ही हम यूज करते हैं उसको, राइट. डिस्ट्रीब्यूटिव प्रॉपर्टीज टुगेदर विद ऑल दीज थिंग्स, ये सारी प्रॉपर्टी हो गई सेटिस्फाइड. देयरफॉर z विद ऑपरेशन एडिशन एंड मल्टीप्लिकेशन इट इज अ रिंग. इज इट ओके? अगर आप नोटिस करोगे z विद ऑपरेशन मल्टीप्लिकेशन, ना तो हमने आइडेंटिटी की बात की कि आइडेंटिटी एग्जिस्ट करना चाहिए, ना ही हमने इनवर्स की बात की, ना ही कम्यूटेटिविटी की बात की, राइट. इन सब के लिए अपन अलग से रिंग को नाम देंगे. अगर लेट्स से मल्टीप्लिकेशन के रिस्पेक्ट में आइडेंटिटी एलिमेंट एग्जिस्ट करता है, वी कॉल इट एज अ रिंग विद यूनिटी. ओके, अगर मल्टीप्लिकेशन के रिस्पेक्ट में लेट्स से कम्यूटेटिविटी है, राइट, देन वी कॉल इट एज ए रिंग, कम्यूटेटिव रिंग, राइट. अगर लेट्स से दोनों चीजें हैं, आइडेंटिटी एलिमेंट भी है और यूनिटी भी है, देन वी कॉल इट एज ए रिंग विद यूनिटी. ओके, एंड अगर हर एक एलिमेंट के पास मल्टीप्लिकेटिव इनवर्स भी है, जब मैं हर एक बोलता हूं इट मींस दैट एक्सेप्ट नॉन जीरो, एक्सेप्ट जीरो एलिमेंट, राइट. हर एक नॉन जीरो एलिमेंट, क्योंकि जीरो के पास तो कभी भी मल्टीप्लिकेटिव इनवर्स नहीं होगा, है ना. तो अगर हर एक नॉन जीरो एलिमेंट के पास मल्टीप्लिकेटिव इनवर्स भी है तो उसके लिए अलग से स्पेशल नाम है, दैट रिंग वी कॉल इट एज ए फील्ड, राइट. तो वो सारी चीजें अपन डिस्कस करेंगे. लेट्स लुक एट सम मोर एग्जांपल्स. So z with operation addition and multiplication, this is a ring. And let me consider one more. In the same way, if you look at, let me say, R set of real numbers with operation addition and multiplication, this is also a ring. Set of rational numbers with addition and multiplication, this will also be a ring. Set of complex numbers with addition and multiplication, usual addition and multiplication, this is also a ring. Zn you are already familiar, you must know about Zn with the operation addition modulo n and multiplication modulo n. This is also a ring. They are all rings. They are all rings. You can easily verify that they are all rings, right? Okay, so this is about the ring, and these are some examples. If you want, you can look at some more examples. Let me consider one more. If we consider, let me say MNR with the operation addition and multiplication. This is also a ring. This is also a ring. Why this is a ring? Where this is matrix addition. What is this? This is matrix addition. Okay, and what is this? This is matrix multiplication. Matrix multiplication. Now you can verify all the properties. Multiplication, right? You can verify that. What is MNR? Let me write it. MNR is nothing but, and इसको और भी generalize कर सकते हो. Let me consider MNF. F is any field, right? Why R consider करना है, right? किसी भी field में consider करोगे, it will be a field. Where MNF, this is the set of all n cross n matrices. N cross n matrices whose entries are coming from F, whose entries are coming from F, coming from field F, field F. Now you can easily verify that this is a field. You can check that MNF with operation addition is an abelian group. MNF with operation multiplication, it is a semi group. Easily you can check all the properties, and MNF with the operation addition and multiplication, it will satisfy all the distributive properties. So it is a ring. This is also a ring. Okay, so this is all about this lecture. In the next lecture we will discuss some more examples of ring. Okay, and we will talk about the what is commutative ring, what is commutative ring with unity, and some more examples. Okay, so thank you everyone, and I will wind up this lecture. See you in the next lecture. Take care. Hello everyone. So in this video we will discuss some more examples of the rings. We have already seen some examples of the ring like Z with operation addition. These are the examples, some examples that we have already seen like Z with operation addition and multiplication. This is a ring, right? Set of real numbers with operation addition and multiplication. Set of complex numbers with operation addition and multiplication. Right, set of rational numbers with operation addition and multiplication. There are some examples of the ring, right? Examples of the ring we have already seen, right? Of the ring we have already seen. कुछ और एग्जाम्पल्स के बारे में इस लेक्चर में अपन बात करते हैं जो इनसे हट के हैं, राइट? ये तो है हमारे पास एग्जाम्पल्स रिंग के. लेट मी कंसीडर Zn, राइट? Example, or let me write number 1. So you can consider Zn with addition modulo n and multiplication modulo n. This is also a ring. It has all the properties of a ring, right? Ring के लिए क्या होना चाहिए? मैं फिर से एक बार रिकॉल कर देता हूँ. R with operation addition and multiplication. R एक non-empty set है. Together with two operations addition and multiplication, we say that it is a ring if it has two properties, mainly two properties, right? I would say three properties, right? The first one is R with operation addition and addition. This should be abelian group. This should be abelian group. ये abelian group होना चाहिए. The second property is R with operation multiplication. ये कैसा होना चाहिए? आपका semi group होना चाहिए. This should be semi group, है ना? And the third one is distributive properties. Distributive properties. Distributive properties. ठीक है. सो अगर इसमें आप नोटिस करोगे तो फर्स्ट एंड थर्ड इस रिंग में ऑलरेडी आपको पता है कि ये सेटिस्फाई होती है प्रॉपर्टी, राइट? व्हाट डज इट मीन? इट मींस दैट Zn विद ऑपरेशन एडिशन मॉडुलो एन, साइक्लिक ग्रुप्स आपने पढ़े होंगे। तो जब रिंग थ्योरी मैंने स्टार्ट किया था, आई टोल्ड यू दैट द प्रीरिक्विजिट्स फॉर द रिंग थ्योरी आर ग्रुप थ्योरी, राइट। तो रिंग थ्योरी पढ़ने से पहले भी सपोज दैट कि आपको ग्रुप थ्योरी आता है। सो दिस Zn विद ऑपरेशन एडिशन मॉडुलो एन, दिस इज एन अबेलियन ग्रुप, दिस इज एन अबेलियन ग्रुप, ये सबको पता है ऑलरेडी, दिस इज एन अबेलियन ग्रुप, है ना। नाउ Zn with operation multiplication, this should be semi group, that we can see. Zn with operation multiplication, it should be semi group, and this is a semi group, right? हमने यूएन ग्रुप पढ़ा, ग्रुप ऑफ यूनिट्स। Zn में से ही हम क्या करते हैं, उन एलिमेंट्स को कंसीडर करते हैं जिनके पास मल्टीप्लिकेटिव इनवर्स हो, है ना। बट Zn के पास बाकी सारी प्रॉपर्टीज होती हैं, मल्टीप्लिकेटिव इनवर्स के अलावा सारी प्रॉपर्टीज होती हैं, मतलब ये सेमी ग्रुप ऑलरेडी है। ग्रुप नहीं बनता है तो ग्रुप बनाने के लिए हम क्या करते हैं, वो एलिमेंट्स को कंसीडर करते हैं जिनके पास मल्टीप्लिकेटिव इनवर्स हो। सो इट हैज प्रॉपर्टी टू बी ए सेमी ग्रुप। व्हाट वी नीड इज द फर्स्ट प्रॉपर्टी इज द क्लोजर प्रॉपर्टी, राइट। इट शुड बी क्लोज विद रिस्पेक्ट टू मल्टीप्लिकेशन, एंड वी ऑल नो दैट a multiplication n modulo b will be inside Z and for all a comma b belongs to Zn. Why is this so? Because whenever you consider the product of any number you can even outside the Zn also, you can consider any integer and you multiplying them, then you are considering the modulo. Anyway, eventually we are considering the modulus n, right? Multiplication modulo n, then it will give you the remainder will be from 0 to n, and 0 to n it will be inside Zn. So anyway, it is closed with respect to multiplication modulo n. And now if you note that we have associativity also, addition multiplication modulo n, b multiplication modulo n, c multiplication modulo n, and c is same as a multiplication modulo n, b multiplication modulo n, c, and for all a comma b comma c belongs to Zn. This is very clear that it is true, right? In general, the multiplication is associative, so the multiplication modulo n is also associative, right? In multiplication modulo n, we only need to take the remainder, right? Other things are similar with the multiplication, not similar, exactly same as the multiplication, right? By multiplying, after multiplication, just we need to take the modulus, right? So it is a semi group. Now, the next property is distributive properties. In Zn, see, in Z we have distributive properties, and with respect to addition and multiplication we have distributive properties. Because of that, with respect to addition modulo n, multiplication modulo n also have distributive properties. So simply you can say that clearly Zn with operation addition modulo n and multiplication modulo n has distributive properties, all right. So we have all the things whatever we need. So it is a ring, right? Zn with operation addition modulo n, multiplication modulo n is a ring. A group तो होता ही था, but together with multiplication modulo n operation, it is a ring as well. Let me consider one more example. Zi. This is called the ring of Gaussian integers, Zi. This is defined as a plus I. Actually, the motivation behind the Zi is, you have seen what is set of complex number. How we define a set of complex number? It is a plus ib, where a and b are coming from real numbers, right? So this is how the set of complex number is defined. तो उन्होंने क्या किया कि a, b belongs to real number की जगह पे what we do is we will consider a, b belongs to z. Then it will something they will be complex numbers, पर जो भी आप a b कोफिशिएंट ले रहे हो they will be integers only, right? वो real numbers जरूरी नहीं, वो fractional नहीं हो सकते, वो आपके irrational numbers नहीं हो सकते. So how this look like? a plus bi और ib लिखने से a plus ib, where a and b are integers, a b belongs to z. This is how the zi is defined. Now you can prove that this is a ring, and let me first define the addition operation. A1 plus ib1 plus a2 plus ib2. From the addition of complex number you must have the idea, right? a1 plus a2 plus I times b1 plus b2, and then multiplication how we define a1 plus ib1, a1 plus ib1 into a2 plus ib2. This is defined as a1 a2, and when we multiply b1 b2, and because of I square this will give minus 1, so minus b1 b2 plus I times a1 b2 plus b1 b2 plus b1 a2 actually. plus b1 a2. This is how the multiplication is defined. Multiplication is similar with the multiplication of complex numbers. Real part will be separated, complex part will be separated. With this addition and multiplication, zi, with the above addition and multiplication, with this addition and multiplication is a ring, right? And this ring is called a ring of Gaussian integers. This ring zi is called ring of Gaussian integers. Ring of Gaussian integers. Okay, fine. Now let's look at this, why this is a ring. Is it have all the properties? Do we have all the properties whatever we needed? So first property is zi with operation addition, it should be a abelian group, right? The first property you can verify easily, that zi with operation addition, this is an abelian group. Okay, in short, let me verify that this is an abelian group. So whenever you add this, right, let me consider a1 plus ib1 plus a2 plus ib2. What is this? This is nothing but a1 plus a2 plus ib1 plus b2. Okay, when you say that this belongs to zi, when you say that this belongs to zi, means what? This a1 and b1, they are coming from z, right? When you say that this also belongs to zi, means a2 and b2, they are also coming from z. So what you can say is a1, a2, b1, b2, they all are coming from z. They are all are integers, right? So जब a1 और a2 integer है, then a1 plus a2 will also be an integer. b1 or b2 integer है, then b1 plus b2 will also be an integer. This will be integer. And when a1 plus a2, b1 plus b2 are integers, so this is an element of zi. So it is closed with respect to addition. The next property is associativity, and we will have associativity because z has associativity. Ultimately, what you are doing? You are doing the addition inside the integers, right? What is this? This is nothing but the addition in z. This is what? What is this? Again, addition inside z. So associativity will be there, and if you want to write, you can write it as a1 plus b1i, and let me say plus a2 plus b2i, and let me consider one more, plus a3 plus b3i. This will be same, as it's very easy to see that a1 plus b1i or ib1, let me say ib1, and plus we have written, let me write in this way, ib1. Okay, a2 plus, let me say ib2, and a3 plus ib3. See, things are same, but it will look good when we write ib1, right? So a1 plus ib1 plus, you consider a2 plus ib2, and plus a3 plus ib3. Okay, so it will be same. It's very easy to see that. So we have associativity. The next property is existence of identity. Then 0 plus 0i, which is same as 0, belongs to zi, is the additive identity. Means 0 is the additive identity, and it's very easy to see that identity. Why? Because if you add this 0 to any number of zi, it will again give you the same, exactly same number, right? If you consider any number a plus ib, you add 0 plus 0i, again we will get a plus ib, right? For any a plus ib belongs to zi. So this is an identity element. The next property is existence of inverse. Whenever we consider a plus ib belongs to zi, we will have minus a minus ib, you can say, or minus b, let me say, into I, or anyway you can write it as minus a plus I times, let me say, minus b. It is same as minus a minus bi, right? So let me write in this, we have minus a minus ib belongs to zi, right? Such that a plus ib plus minus a minus ib is equals to 0. So this will give you identity element. It means that it has inverse, additive inverse with respect to additive inverse for any element a plus ib inside zi, right? Now अभी आप नोटिस कर सकते हो, अगर ये zi का एलिमेंट है, what does it mean? It means that a and b are the integers, then minus a minus b will also be an integer, so this is also an element of zi. It means that in zi every element a plus ib has additive inverse. The next property is commutativity with respect to operation addition. What does it mean? It means that if we consider any element a1 plus ib1, let me say a1 plus ib1 plus a2 plus ib2, this is equals to a1 plus a2 plus I times b1 plus b2, and we can also write this as a2 plus a1 plus I times b2 plus b1, because anyway the addition is inside z and it is commutative. So, and now we can write this as a2 plus ib2 plus a1 plus ib1, and this we can write. Is that okay? Now we can say that this is commutative, right? It has commutativity. Or you can say that zi with operation addition, zi with operation addition is an abelian group, So this is an abelian group. Is that or not? Alright. So now the next property is zi with operation multiplication. It should be semi group. Zi with operation multiplication. Let's look at the first property, is closure property, and by definition it is closed. You want to write it, you can write it. See this. When we say that these two elements are coming from Z, means a1, b1, a2, b2, they all are integers. And when a1, a2, b1, b2 all are integers, then a1, a2 minus b1, b2 will also be an integer. a1, b2 plus b1, a2, this is also an integer. And when these two are integers, then this complete number is also a member of Zi, right? It is also a Gaussian integer. So clearly we can see that we have closure property. So let me write it. a1 plus ib1 into a2 plus ib2 is equals to whatever it is. Let me write this belongs to zi. This belongs to zi for all a1 comma b1, or let me say for all a1 plus ib1 and a2 plus ib2 belongs to zi. It's very easy to see that. I told you right how it is. Since, let me write, since if a1 comma a2 comma b1 comma b2 belongs to z, then a1, what was the multiplication? a1 a2 minus b1 b2, then a1 a2 minus b1 b2 and a1 b2 plus b2 a1, right? Also, then this and this are also integers, that's why, right? So it is closed with respect to multiplication, and it will have associative property also, because ultimately we are doing the multiplication inside integers, right? Okay, where whatever number you consider, a plus ib into c plus id, anyway we multiply inside z, right? And then we are separating the real part and the imaginary part in the sense, right? So we will have associativity also. You can verify that we will have associativity with respect to multiplication. Associativity with respect to multiplication, and why it is with respect to multiplication? Since, or you can say that because z with operation multiplication is associative. After, let me say, because z has associativity with operation multiplication. Associativity with operation multiplication, and the same argument is for distributive properties. Okay, same argument for distributive properties. Same argument for distributive property. What does it mean? It means that zi will have distributive properties because z has distributive properties with the usual addition and multiplication. It's very easy to see that, because anyway when we are doing multiplication or addition, right? You take two numbers from Zi and you do multiplication or addition inside Zi. Ultimately, we are doing addition and usual addition and multiplication inside Z. And Z has distributive properties and everything whatever we need to be to be a ring, right? So that's why Zi, therefore what we can say is Zi with operation addition and multiplication is a ring. More than that, being a ring, it is a commutative ring actually, and commutative ring with unity. It is a CRU. What is a commutative ring? What is a commutative ring with unity? What is a unity? All these things we will discuss in the next lecture. Okay, so this is all about this lecture. Thank you. Happy learning. Take care and bye bye. Okay, in this video, let's see what is commutative ring with unity, or in short we say that a CRU. Commutative ring with unity or a CRU. To see for what is commutative ring with unity, let's first see what is commutative ring. Let me write what is commutative ring. Okay. Let's say we have a ring R with operation addition and multiplication. Let R with operation addition and multiplication be a ring. We say that it is commutative ring. We say that R with operation addition and multiplication be a commutative ring. Be a commutative ring if multiplication operation is commutative on R. If multiplication is commutative on R. Okay, what does it mean? See, R with operation addition and multiplication, to be a ring, the first property we need is R with operation addition should be abelian group. It means that the commutativity for addition operation is by default it should be there, right? There is nothing special, huh? But for multiplication we do not need commutativity to be a ring. मतलब अगर ring है तो जरूर नहीं कि multiplication के respect में commutativity है तो अच्छी बात है, नहीं है तब भी वो ring हो सकता है. But if it has multiplicative commutative with respect to multiplication, what I mean is, if R has commutativity with respect to second operation, whatever second operation is, here it is multiplication. Call this second operation as multiplication, we call this second operation as multiplication. So whenever we have commutativity with respect to second operation, we say that the ring is commutative. Okay, so that is what we say is, that is R with operation addition and multiplication is a commutative ring, a ring if A multiplication B is same as B multiplication A for all A comma B belongs to R, right? सेकेंड ऑपरेशन के रिस्पेक्ट में भी, क्योंकि फर्स्ट के तो रिस्पेक्ट में पहले से ही है, और सेकेंड ऑपरेशन के रिस्पेक्ट में भी कम्यूटेटिविटी है, वी कॉल इट एज अ कम्यूटेटिव रिंग. एंड द सिंपल एग्जांपल वी कैन हैव इज Z with operation addition and multiplication is a commutative ring, right? It is a commutative ring. Why this is a commutative ring? Because it has commutativity with respect to second operation also. You multiply any integer A and B, or you multiply B with A, it's same for all A comma B belongs to Z, right? That's why it has commutativity with respect to second operation, so it is a commutative ring, right? We can have some more examples, right? You can consider, let me say, Zn with operation addition modulo n multiplication modulo n. It is also a commutative ring. This is also a commutative ring, right? We can consider, let's say, 2Z, right? 2Z with addition, usual addition and usual multiplication. This is also a commutative ring, right? You consider any number of the type 2m into 2n, right, where m comma n belongs to z. This is same as 2n into 2m. For all 2m, let me say, comma 2n belongs to 2z. So it has commutativity. They are the commutative rings. Now let's define what is commutative ring, commutative, or let me say ring with unity. Right? What is a ring with unity? A ring with unity. अगर आपने ऑब्जर्व किया होगा, रिंग डिफाइन करने के लिए फर्स्ट ऑपरेशन के रिस्पेक्ट में आइडेंटिटी होना चाहिए, क्योंकि फर्स्ट ऑपरेशन के रिस्पेक्ट में उसको ग्रुप बनना है, बट द सेकेंड ऑपरेशन के रिस्पेक्ट में हमने कोई बात नहीं कि आइडेंटिटी होगा या नहीं होगा. अगर सेकेंड ऑपरेशन के रिस्पेक्ट में कम्यूटेटिविटी है, वी से दैट कम्यूटेटिव रिंग, इट्स ए कम्यूटेटिव रिंग. और अगर सेकेंड ऑपरेशन के रिस्पेक्ट में आइडेंटिटी एलिमेंट है, देन वी से दैट इट इज अ रिंग विद यूनिटी. ओके, लेट मी राइट डाउन द फिगर. सपोज R with operation addition and multiplication is a ring. Let R with operation addition and multiplication be a ring. We say that R with operation addition and multiplication is a ring with unity, is a ring with unity if there exists E belongs to R, let me say E belongs to R such that R precisely I would say 1 belongs to R. Okay, if क्योंकि मल्टीप्लिकेटिव आइडेंटिटी को हम जस्ट नोटेशन यूज करते हैं एज अ 1, राइट. यूजुअल मल्टीप्लिकेशन के रिस्पेक्ट में 1 ही मल्टीप्लिकेटिव आइडेंटिटी होता है, 1, बट 1 इज हियर जस्ट अ नोटेशन, राइट. किसी भी रिंग में अगर मल्टीप्लिकेटिव आइडेंटिटी है उसको हम 1 बोल देते हैं. इट इज द 1 R, यूनिटी ऑफ द रिंग. ओके, 1 belongs to R, there exists 1 belongs to R such that 1 into R is equals to R into 1 is equals to R for all R belongs to R. Okay, this element R is this element 1 is called, if it exists, right, you should keep this in mind, right. So this element 1 is called the unity element of R, or the unity element of R, right. What does it mean? The identity with respect to second operation is called the unity element if it exists. You should write it if it exists, right. When we are defining a ring with unity, it means that there are some rings which are not ring with unity actually, right. So let's take some examples. If we consider our first example can be ring with unity is Z with operation addition multiplication. It is a ring with unity, right. In the previous one, commutative rings, I think we should consider some non-examples as well. Let me write it. The fourth example we can consider, which is not actually a commutative ring, and we can consider M2R, right, set of all 2 cross 2 matrices whose entries are coming from real numbers with operation addition and multiplication. What is addition? Matrix addition. Multiplication is nothing but matrix multiplication, right. So this is matrix addition. Let me write it. Matrix addition. And what is this? This is matrix multiplication. Multiplication. So if you look at this ring, this is not a commutative ring. This was not a commutative ring. Not a commutative. Why it was not a commutative ring? Because the matrix multiplication in general, it is not commutative, right. So with respect to second operation, it does not have commutativity, right. Since you can write, since A multiplication B is not same as B multiplication A for all A comma B belongs to, or you can also say that A multiplication B is not same as B multiplication A for some A comma B belongs to M2R. I'm not saying that for all, because if you say for all, it means that there is no element which can commute together, right. It's not like that. There are matrices which commutes with every element, like scalar matrices, identity matrix, and many more. Okay, so what is ring with unity? We have seen the definition, and this was our first example, said with operation addition and multiplication. Why it is the example of ring with unity? Because it has a element it has an integer which multiplies with any integer, it will give you the same integer, the original integer, right? So if I consider any integer, let me say m, and we multiply with 1, what we get is, and it is same as 1 into m is equals to m for all m belongs to z. What does it mean? It means that 1 is the multiplicative identity of this ring. So 1 is the unity, let me say, right? Unity of z with operation addition and multiplication. So it is a ring with unity, right? Let's look at some more examples. If I ask you, let's say, power set of n with symmetric difference and intersection operation, what do you think? Is it a ring with unity? Is there some subset of power set of n such that if we take the intersection, because we need to take the second operation, right? So whenever we take the intersection with that element of the power set of n, and it should again give the identity element, right, or the same element whatever we have considered. So what does it mean is, if we consider, let's say, a belongs to power set of n, right? Now we are looking some element of power set of n such that if we consider a intersection with that element, let me call that element for the time being as e, okay, and a intersection e should be same as a for all a belongs to power set of n. And when we say that a belongs to power set of n, it means that a is actually a subset of n, right? So ऐसा कौन सा पावर सेट ऑफ n का एलिमेंट हो सकता है या फिर n का सबसेट हो सकता है जिसका किसी भी n के सबसेट के साथ हम इंटरसेक्शन लें, देन अगेन हमें a मिल जाए? व्हाट डू यू थिंक? द नेचुरल गेस इज वी कैन कंसीडर सेट ऑफ नेचुरल नंबर इटसेल्फ, राइट? क्योंकि नेचुरल नंबर ही सबसे बड़ा सेट है, उसका n का सबसेट n ही है, जिसके साथ किसी का भी इंटरसेक्शन लेंगे इट विल गिव यू द सेम एलिमेंट, राइट? सो हियर e इज एक्चुअली e इक्वल्स टू, सो ऑब्जर्व दैट e is equals to actually n, right? So whenever you consider a intersection n, or let me say n intersection a, this will be a for all a belongs to power set of n. Is that or not, right? So therefore what we can say is, therefore n belongs to power, and it is belonging to power set of n, right? Because it is also a subset of n. So n belongs to power set of n is the unity element of, unity element of power set of n with symmetric difference and intersection operation. Is that or not, right? So this is a unity element, and therefore it is a ring with unity. So this is a ring with unity. It is also a ring with unity. Now let's look at some non-examples where we have a ring and which is actually a ring but it is not a ring with unity. So we can consider this ring. Let's say 2z, we have considered, right? 2z with operation addition and multiplication. It is not a ring with unity, Why this is not a ring with unity? Because there is no element inside 2z which can multiply it with any element and it should give again the same element. There is no element in 2z. Because यूजुअल मल्टीप्लिकेशन के रिस्पेक्ट में क्या हो सकता है, एक नेचुरल गेस की क्या मल्टीप्लिकेटिव आइडेंटिटी हो सकता है, किसी के साथ में मल्टीप्लाई करा वही हमें इंटीजर मिल रहा है, दैट कैन बी 1, राइट? बट 1 इज नॉट देयर इनसाइड 2z, राइट? 1 नॉट बिलोंग्स टू 2z, therefore 2z does not have unity element, and so it is not a ring with unities. It means that we have some rings which are not actually ring with unity. Now let me define, okay, let me consider a few more examples and then we will stop. If I consider, let me say, an example which is actually a commutative ring but it is not a ring with unity, so we can consider 2z, this we can consider, right? So you can note that, let me write as observations, right, as a point. So if you note that 2z with operation addition and multiplication, it is a ring, commutative ring but without unity, commutative ring without unity, unity. Okay, in the same way we can have a ring which has unity element, but it is not commutative. And you can guess what can be this some example. We can have a lot of examples, but the simplest example we have already seen, it is M2R with operation addition, matrix addition and matrix multiplication. This is actually a ring with unity, which is non-commutative ring with unity. It is not commutative, but it has unity element. It is a non-commutative ring with unity. Commutative ring with unity. Why we are discussing this point? Because there are rings which has commutativity but not unity. There are rings which have unity but not commutativity. But if we have both the properties together, if there is a ring which has unity and commutativity both, we say that it is a commutative ring with unity, and that ring is called as a CRU, right? Why this was not it has unity. I think non-commutativity is very clear, we have discussed, and the unity element is I equals to 1 0 0 1. This identity element is the unity. This is the unity of M2R. Right? Okay, now let me define what is commutative ring with unity. What is commutative ring with unity? Commutative ring with unity, and in short we say that CRU. Right? I think definitions should be clear to you, and you can write it by yourself as well. So what is the definition of commutative ring with unity? A ring is commutative ring with unity if it has commutativity as well as unity, right? So let R with operation addition and multiplication be a ring. We say that R with operation addition and multiplication is a commutative ring with unity, a CRU, if it is commutative ring, if it is a commutative ring with unity, if it is a commutative ring and it's a ring with unity as well, it's a ring with unity as well, ring with unity as well, then we say that it is a commutative ring with unity. What we can say that it means that is R with operation addition and multiplication is a CRU, commutative ring. We are already considering that it is a ring, then we say that it is a CRU if it has following properties. If first property is A multiplication B is same as B multiplication A for all A comma B belongs to R, and the second is there exists, let me say, E belongs to R such that EA is equals to AE multiplication, right? Multiplication E is same as A for all A belongs to R. If it has these two properties, then it is a commutative ring with unity. Let's look at some examples. And the best example we can have, we have already seen some examples already, right? The first example can be Z with the operation addition multiplication. It is a CRU, commutative ring with unity, right? Because this example was in the both definitions, right? In the commutative ring also, in the ring with unity also. So it has both the things, right? It has commutativity, it has ring with unity, right? It has unity element, so it is a commutative ring with unity. This can also be an example. Zn with operation addition modulo n and multiplication modulo n. This is also a CRU, commutative ring with unity. We can have many examples, and we will discuss in detail in the next lecture. So you can consider Zi with operation addition and multiplication. This is also CRU. Right, we can have let me say power set of n with symmetric difference and intersection operation. This is also CRU. You should verify it by yourself first. You should look at all these things, why this is a CRU, and in the next lecture we will discuss some more examples of CRU, and we will discuss about these examples why they are CRU. Okay, so this is all about this lecture. Thank you, happy learning, take care, and bye bye. In this video, we will discuss in detail the examples of CRU. What are some examples? We have already seen some examples of CRU, right? Let me recall those examples. And the examples was, we have seen Z with operation addition and multiplication, it is a CRU. In the same way, when Z is operation addition, multiplication, it is a CRU, we can have a lot. Like you can consider, let me say Q with operation addition, multiplication. It is also CRU, commutative ring with unity. It has commutativity with respect to operation, and there is nothing to verify in these examples, right? I will skip this and you can verify. And actually there is nothing to verify, because with respect to multiplication, one is there inside rational numbers, one is there inside Z also, so it has unity, and multiplication is anyway, it is commutative, right? And the third example can be consider R with operation addition, multiplication. This is also CRU. You can consider set of complex numbers also with operation addition and multiplication. Right, this is also CRU. Multiplication is commutative and it has one unity with respect to multiplication, so it is also CRU. Now let's look at some more examples. We have seen a power set of n. You can write power set of n with symmetric difference and intersection operation. This is a CRU. Now let's look at this, why this is a CRU. The first thing you should keep in mind is that the intersection, the second operation. Here it is not multiplication, but you should keep in mind whenever we say that multiplication, right? It means that we are talking about the second operation, right? Otherwise, it will be a problem for you. I told you in the beginning as well that multiplication means it is just a notation for the second operation. It can be any operation if it has properties similar with the multiplication, okay? So like intersection here. So when we say that it has commutativity, it means that with respect to intersection operation, it means that whenever you consider two subsets of power set of n, two elements of power set of n, let me say A intersection B, and we know that a B intersection A is same as A intersection B. We all know this, right? From set theory, there is nothing to verify with this. A for all A comma B belongs to power set of n. It means that it has commutativity. When it has commutativity, let's look at the identity element, and identity with respect to second operation. And I think we have discussed this, right? So we know that we have n belongs to power set of n such that A intersection n is same as A, or you can also say that n intersection A for all A belongs to power set of n. It means that this n, that is n belongs to power set of n, is the unity element, right? So it is a ring with unity. It is a commutative ring with unity. We have seen Zi with addition and multiplication. What is addition and multiplication? We have seen, right? So this is also CRU, commutative ring with unity. Why this is a commutative ring with unity? Because multiplication is commutative. If we consider A1 plus IB1, and let me say multiplication A2 plus IB2, this is same as A2 plus IB2, and multiplication A1 plus IB1. You can check that. So this is same, right, for all A1 plus IB1, and A2 plus IB2 belongs to Zi. So it has commutativity. It has commutativity, and 1 is there, right? 1 belongs to Zi. Maybe सारे आपको एलिमेंट Zi का ना दिख रहा हो, पर अगर आप ऐसे डिनोट करो कि 1 plus 0i belongs to Zi, and it has property 1 plus 0i into A plus IB, or A plus IB into 1 plus 0i is equals to A plus IB for all A comma B belongs to Zi, right? So it is also a CRU. We can have some more examples. We can consider, let me say, just give me a minute. Okay, I think we should discuss some non-examples as well. We have seen in the previous lecture also, but let me again recall this example. So if I ask you mz, what do you think when mz is a mz? Let me write as a question. Mz is a CRU, if and only if, what do you think? Let me say, first option is m equals to 0, and the second is m is prime. Let me say m is prime. If and only if, you should keep in mind that if and only if, right? And the third is m is not equals to, let me say 1, m equals to 1 or minus 1, and let me say 1 or minus 1, or let me say 0, and the fourth is m is not equals to 1 comma minus 1 comma 0. So what do you think? mz is a CRU if and only if. What are those conditions? So if you look at C, if let's say m is 0, then it is a CRU, that is clear, but the condition is if and only if, and that cannot be a CRU if m is not equals to 1. M is not equals to, that is not correct actually, right? There are, if you consider, let's say m equals to 1, if m equals to 0, first let me see, if m equals to 0, then mz is nothing but equals to only 0, and it is a CRU, that is correct. But if you consider, let's say, if m equals to 1, then mz will be nothing but z, and this is also CRU. So if you consider 1 also, then it can be, so if and only if this is not correct. Again same, m is prime, 1 is not a prime number, and 1z is a CRU, so this is not a if and only if condition, right? Even if m is not a prime number, then also it can be a CRU, so that is correct. And if you consider, let's say, m equals to 1, minus 1 and 0, that is correct, it will be a CRU. We have seen this. If you consider m equals to minus 1 also, then it is a CRU. mz is equals to minus z, and this is actually z. Minus z is what? Again it is z. Okay, and this is also CRU, commutative ring with unity. So 0, for 0, 1 and minus 1 values of m, it is a CRU. Except this, if you consider any m, let's say, if we consider, let me move to next page. If, let's say, if m is not equals to 0, minus 1 or 1. So whenever you consider mz, 1 will not belongs to mz, right? For all m not equals to 0, comma minus 1, comma 1, it will not have. And one more thing you should keep in mind, I think we should remove this 0 from here. So this is, anyway it is not correct because m equals to 0. This is not a CRU actually. This is not a CRU. I'm really sorry. What is this? This is not a CRU. Because whenever you say unity element, I think we should define in the definition itself. The unity element is always different. Let me write as a note here. Unity element is different, or it should be different. Unity element should be different from the identity with respect to first operation. Identity with respect to first operation. First operation, right? What does it mean? It means that here, if you look in 0, it has only 0 element, but the unity should be, and this is an additive identity, so unity should be different from 0, but there is no element except 0. That's why this is not actually a CRU. So this was not correct. And here, if we consider m equals to 1 minus 1, then we can say that for m, if m is not equals to minus 1 comma 1, then 1 will not be there. If you consider 0, तब तो नहीं है. 0 के अलावा अगर कोई भी 1 minus 1, अगर आप कंसिडर 0 से 1 से बड़ा लेट्स से, या फिर minus 1 से छोटा कोई इंटीजर कंसिडर करते हो, क्या लगता है आपको होगा? अगर लेट्स से 0 minus 1 से बड़ा क्या 2, 3, 4 ऐसा कुछ कंसिडर करोगे, -2, -3, -4, तो उसमें 1 आएगा क्या? कभी सारे मल्टीपल्स होंगे. लेट्स से 2 आपने कंसिडर कर लिया, देन ऑल द मल्टीपल्स ऑफ 2, 1 इज नॉट अ मल्टीपल ऑफ 2, राइट? तो 1 आपको कभी भी नहीं मिलेगा. फॉर ऑल m not equals to -1 comma 1, then this option is correct. So mz is a CRU if and only if m equals to 1 or -1. Otherwise, it will not be a CRU. This will also be a discarded, right? m is not equals to 1 -1, ये तो obviously गलत है क्योंकि m equals to 1 के लिए CRU है. I think अभी clear होगा कि what does it mean by a CRU, है ना? So I think these are the some examples. जैसे आगे और आप पढ़ोगे तो और भी बहुत सारे examples आपको दिखेंगे CRU के, commutative ring unity के, ठीक है? नॉन एग्जाम्पल्स के अगर हम और बात करें, so we can have, let me say, M2R, राइट। ये आपका क्यों नहीं बन रहा, जैसे 2Z आपने कंसीडर किया, इट हैज कॉम्यूटेटिविटी बट इट डज नॉट हैव यूनिटी एलिमेंट, राइट। ये आप थोड़ा सा नोटिस कर लो। 2Z with operation addition and multiplication, this has commutativity but not unity, commutativity but not unity, right। एंड अगर इसको आपने देखो, ये भी CRU नहीं है, सो इट इज नॉट ए CRU। इन द सेम वे CRU ये भी नहीं है, दिस इज आल्सो नॉट ए CRU। पर ये किसकी वजह से नहीं है, ये कम्यूटेटिविटी की वजह से नहीं, ये यूनिटी की वजह से नहीं था, ये कम्यूटेटिविटी की वजह से नहीं है ना। M2R दिस इज नॉट ए CRU बिकॉज M2R with addition and multiplication has unity, actually has unity but not commutativity, has unity but not commutativity, that's why this is not a CRU, okay। So these were the examples, and as we move ahead we will see some more examples of commutative ring with unity. And commutative ring with unity, they are actually important. Whenever we talk about ideals, we consider commutative ring with unity. एंड इन द नेक्स्ट जब भी हम आगे बात करेंगे कभी भी रिंग के बारे में, वी विल कंसिडर कम्यूटेटिव रिंग विद यूनिटी बिकॉज एवरी इंटीग्रल डोमेन इज आल्सो a CRU. So until otherwise stated, ring is not a CRU. You have to consider by default it is a CRU. Whenever we say that it is a ring, it means that I will mean that it is a CRU, right? Whenever we say that precisely that it is not a CRU, then you consider only it is not a CRU, otherwise you can consider it as a CRU, okay? So this is all about this video. In the next lecture we will discuss some upcoming things like what are the unit elements and some more things, okay? So we will stop here. Thank you, happy learning, take care and bye.